Good evening, I'm SUPRAGNA. I'll be discussing about the design methodology in IoT. Here we can see all the 10 stages in this diagram. Now I'll be explaining a little about each stage. First we have purpose and requirement specifications. This is the initial stage that defines the core of our IoT system. Next we have process specification. In this stage we outline the overall flow of data. Next we have domain model specification. Here you delve deeper into the real world entities that involved in our system. Next, we have information model specification. This stage focuses on how data will be structured and formatted. Next, we have service specifications. Here, you specify the functionalities that our IoT system will offer. Next, we have IoT level specification. This stage defines the communication architecture of our system. Next, we have functional view specification. Here, we detail the system's functionalities from a user perspective. Next, we have operational view specification. This stage focuses on the non-functional aspects of the system. Next, we have device and component integration. Here, we bring all the different components together. Next, we have application development. This stage involves developing the user interface and any application that will interact with our IoT system. Next, purpose. In purpose, it monitors water levels, offer remote access. Requirements. Integrate sensors, ensure connectivity and prioritize data security. Scalability and flexibility. Design for different tank sizes, offer customization and ensure compatibility with existing IoT ecosystems. Next we have data handling. It collects sensor data, filter for accuracy, communication, transmit data efficiently. Alert system. Monitor thresholds, generate real-time alerts. Here we can see the flow chart. In this flow chart, it will first, the system checks if the mode is set to automatic. If the mode is automatic, the system checks the water level. If the water level is low, the system turns the pump on. If the water level is not low, the system turns the pump off. If the mode is not automatic, the system notifies the user and waits for a response. Next, here we can see the class diagram. The class diagram shows classes for a control system that manages water tank. The water tank has attributes for its ID and water level. The control system can initialize the tank. Other classes like sensor and motor control interact with the control system to manage the tank. Arrow show methods like adjust water level and show water level to continue the tank. Next, we have domain model. In this, we have physical entity. We have water tank and sensors. In virtual entity, we have thresholds and consumption patterns. And in device, we have sensors and actuators. And then we have resources. They have sensor data and metadata. And in services, we have data analysis. They provide service like for analyzing sensor data for trends or anomalies. And then we have alert generation. Service monitoring data and triggering notifications. And then we have information model. In this we have virtual entity. Here we can see the water level. It's abstract representation of the water level in the time. Attributes. We have timestamp. It indicates the time of the water level measurement and actual water level measurement by using the level value. And relations. We don't have any relationship. Water level may indirectly relate to entities like alerts or consumptions. Next, here we can see the structural information diagram. Well, this is for a home automation, but like we explain it to you how it will be in the point of like water level management system. In classes, we'll be having two classes, water tank and sensors. And then we'll talk about aggregate relationship, the whole part relationship. The water tank is a whole and the sensor is a part of it. A water tank typically has a sensor to function effectively. Lifetime dependencies. The lifecycle of the sensor depends on the water tank. Optional part. While most water tanks might have sensors, it's possible to have a basic tank without that. And next we have service specification. In service type, we have two data collection. It gathers all the real-time water level data, alert generations. It monitors the data and triggers alerts. In inputs and outputs, input is we have sensor data and output is alerts for critical thresholds. And then we have service endpoints collection. This is sensor data and monitor levels and triggers alerts. And in service schedules, we have continuous data collection, event-driven alert generation. And then we have service preconditions, access to sensor data, define alert the threshold. Next, here we can see the diagram. It has like a controller monitors a water tank using a sensor. The controller operates in auto or manual mode. In auto mode, the controller checks the sensors reading every 5 seconds. If the water level is low, the controller turns the pump on. Next, we have IoT level management. Here we have device level integration. Basically, sensors on tanks with limited connectivity. Edge processing. Sensors process data locally, sending aggregated information. Cloud integration. Data sent to cloud for storage and analysis. Advanced analytics and automation. Advanced analytics predict and optimize water usage. Next, we have IoT ecosystem integration. Integration with broader IoT networks for comprehensive water management. And next, this diagram. The system shows a local unit that manages the connected water tank. The controller communicates with a cloud service, possibly for data storage. Sensors provide data, and which may include water level. Based on sensor data and pre-programmed rules, the controller can adjust the device, potentially a pump, to maintain the water level. Next, we have functional view for water level. Data acquisition. Collects real-time data from the sensors for accurate measurements. Next, we have alert generation. Monitors levels, triggers alerts for critical conditions. Next, we have data analysis. Analyzes historical data for usage, insights, and predictions. Then we have remote monitoring and control. Allows remote access, proactive action based on data. We have next system management. Oversees system operation, ensures reliability throughout the entire maintenance. And now here we have web app and database. The system interacts with the web application, and then communication, we have different parts of they communicate through like all the RESTful services and protocols. And then we have application server and management services, and application server handles application logic and interacts with the management services. And then we have sensor data and device management. Sensors provides data on the water tank, likely body level. Resources and communication protocols. Resources like pumps and actuators are managed. Communication protocols enables communication between devices and the system. Next, we have operational use specification. First, we have service hosting. Cloud or on-premises option for hosting services. Storage. Cloud or local storage for sensor data. Devices. Wired. We either have wired or wireless sensors for monitoring, and in application hosting, web or mobile app. We can use either web or mobile application. And then in communication, we have internet or mesh networking for data transmission. Now I'll be discussing about this diagram. We can have like a web app and services. A web application allows user to interact with the system. And in data management, data sensors is stored in a MySQL database. Device management. A Raspberry Pi acts as a computing device. Communication protocols. Communication protocols like TSP or Wi-Fi enables communication between devices and the system. Security. Security measures are in place to restrict access to the web app and database. Next, we have device and component integration. First, we have sensor integration. Connect and configure sensors for accurate and transmission. Gateway integration. Incorporate gateways for local processing and data transmission. Next, we have cloud or server integration. Connect to cloud or server for data. Next, I have validation and testing. Test system components for reliability and performance. Next, we have application. First, we have user interface design. Designing user-friendly interfaces for monitoring and control. Next, we have backend development, developing logic for data processing and communication, mobile or web development, building responsive apps for accessing the system, testing and deployment, testing thoroughly before deployment to production. And next, I'll be discussing about this diagram. This system shows a local controller managing a connected water tank. Sensors likely including a water level sensor, monitor the water tank, and send data to the controller. The controller makes decisions based on sensor readings and pre-programmed rules. The controller can activate a pump to maintain the water level. The users can interact with the system through a web interface. Thank you.
Hello, this is Sasmita from BTech CS SRM, currently pursuing BTech CSC in second year, and today I'm here to teach you the topic embedded systems. Lecture 2. Embedded systems are all around us, from our cars and our appliances to our smartphones and wearables. This presentation will explore the design methodology for embedded systems, computer logic, focusing on microcontrollers and system-on-chip SoCs. We will break down the design process into three key stages: requirements, definition, hardware selection, and software development. So, introducing to you my AI-generated image of embedded computing design methodology. You can look the details, the tiny things on the chip. So this is how they are assembled in the factories through machines, complex machines. Uh, I would just like to share a fun fact before starting this presentation. Uh, like in our country, we recently started setting up the factories to manufacture these chips, which and then it is speculated that this initiative will reduce the price of the gadgets by nearly half. Like the laptop which you buy at 1 lakh will now come for like 50,000. So just look how important these chips are, how they are the game changer in the world, and how they caused a global market shutdown during the pandemic because we couldn't, no one could sell washing machines or cars or whatever because it is in everything. So what is exactly is this embedded system which caused this so much ruckus during the pandemic? So an embedded system is a specialized computer designed to perform a specific task within a larger device or system. It typically has limited resources, processing power and memory, and interacts with the physical world through sensors and actuators. So you can see the explanation through the diagram here. And then how does IEEE define it? So it's IEEE defines it as a part of larger system and which performs the requirements of that system. It's the word embedded itself says that it is like a parasite but not relying on that system, but performing to something for the system. So the embedding system on which this embedded system is mounted is the actual parasite here. So case studies. Example of embedded systems, you can see them in your smartphones and wearables, industrial control systems, where these are the backbone of industrial automation. All the machines in the industries work on the small embedded chips where the specific programs are written, and automotives and IoT devices such as home automation systems, etc. So the characteristics of embedded systems, they have compact and efficient, like they're compact and efficient. They have limited memory and peripherals. They are like packed in a punch in a small frame, and low power consumption. They, since many run on batteries like washing machines and all, they don't have like direct electric supply for the embedded system to work. The embedded system in it works on batteries, so they are designed to be energy efficient, reliable and focused. They have rock solid reliability. Like imagine a heart pacemaker. It has one crucial job and it needs to do it flawlessly. Embedded systems prioritize reliability and stable operation to ensure their tasks are completed accurately. Singular focus. They excel at a specific task. Like they are not the jack of like they're not like jack of all trades, but they're master of one. So it basically is the opposite. And specialized and real time. They are so specialized for the purpose and they have minimal user interface because they generally operate behind the scenes and the user need not even interact with the embedded systems because the user interacts with the embedding system. And the real time performance, the timing is critical actually. Example, the ABS braking system in cars, which constantly monitors the wheel speed. If it detects a rapid deceleration, it intervenes within milliseconds by applying and releasing the brake pressure rapidly. This real-time response prevents wheel lockup and maintains steering control and helps avoid skidding accidents. And additional considerations, these have to be always on and ready. Like for example, the fire alarm should always be on so that it can detect when there's a fire. Built to last, so they're also long lasting devices essentially because they are embedded inside and they're actually safe physically. So the requirements. Embedded system requirements can be broadly categorized into two main types, functional and non-functional. While functional requirements outline the specific actions the system should carry out, they detail what data the system will receive as input and what actions or outputs it should produce. The non-functional requirements, on the other hand, focus on how the system will perform these tasks. They establish criteria for factors like speed, power, efficiency, reliability, safety, and physical limitations like size and weight. Considering both types of requirements ensures the embedding system is not only capable of doing the right things, but also does them in the right way, in the right time, meeting the project's overall goals. Software development. So the embedded system software is a crucial aspect of embedded system design. Embedded systems typically use low-level programming languages like C to provide greater control over hardware interactions, because conventionally the C programming language is used to write many of the operating systems. Like for complex systems, real-time operating systems (RTOS) may be used to manage tasks and resources. The software developing process is like we define software requirements, we design and implement the code, we test and debug. And the code for embedding systems, we have resource constraints like memory and processing power, because since it's an embedded chip, we need to take into consideration the memory it can hold, and the real-time requirements are its constraints during the coding process. Design tools and techniques. Imagine a computer screen displaying an IDE with code editor, debugger, and project explorer windows. So this is how it is developed. Several design tools and techniques can help streamline the embedded system design process. Integrated development environments, IDEs, offer a comprehensive suite of tools for code editing, debugging, and project management. Simulators and emulators allow for testing software. These simulators and emulators can even be virtual or physical sometimes, depending on the urgency or else the significance. So the modular design, like in terms of design techniques, modular design breaks down the system into smaller, more manageable modules. Top-down design starts with a high-level overview and iteratively refines details, while bottom-up design approach focuses on developing individual components and integrating them into a cohesive system. Testing and debugging. Unit testing. So we have different kinds of strategies for testing here. Unit testing is where individual modules are tested in isolation. Integration testing is where modules are combined and tested for interactions. System testing is where the entire embedded system is tested against requirements, like after the integration. And debugging techniques, print statements, and logging for tracing program execution. Debuggers for stepping through code and inspecting variables. Variables are actually essential because they are the things which the UI interacts with. So we as users. So rigorous testing is essential for ensuring the functionality and reliability of these embedded systems. Different testing strategies are employed. Debugging techniques involve using print statements is very crucial here. And our teammate Akshay will continue to take you through the microcomputers and system on chips in lecture 3. And moving on to the contributions, we executed code to generate the imaging plant UML for the class diagram of the design methodology, while my teammate SUPRAGNA executed that for flowchart, and the content we collected was collected from the Edubuzz book recommended by the Anna University, and her content, SUPRAGNA's content was collected from Cisco IoT Fundamentals as well as Edubuzz Anna University book and other online resources. Thank you.
Exploring microcontrollers and system on chips. Microcontrollers are a popular choice for embedded systems due to their compact size, low power consumption, and integration of various functions on a single chip. when choosing a microcontroller for embedded systems, prioritize factors such as processing power, memory capacity, and available peripherals. Ensure the MCU aligns with your project's requirements while considering power consumption and cost effectiveness. A balance between performance and energy efficiency is crucial for optimal functionality, especially in battery powered applications. System on chips. System on chips integrates CPU, memory, peripherals, and specialized processing units onto a single chip, enabling advanced functionality for embedded systems. Their high integration level fosters miniaturization, boosts performance, and improves power efficiency, especially beneficial for tasks needing specialized hardware like GPUs. This facilitates efficient and compact design solutions for various embedded applications. System on chips represent a cutting edge solution for complex embedded systems, offering seamless integration of multiple components and enabling innovation in diverse application domains. Designed for manufacturability. Designed for manufacturability principles ensures efficient and cost-effective production of embedded systems. This includes selecting affordable, readily available components and optimizing board layouts for streamlined routing and assembly. Designing for testability further enhances manufacturing efficiency by facilitating automated testing during production, ensuring product quality and reliability. Additionally, considering DFM principles earlier in the design process can minimize manufacturing delays and reduce overall production costs, leading to a more competitive and scalable product. In conclusion, embedded systems design is a multifaceted process that requires a structured approach. This presentation explored the key stages, including defining requirements, selecting appropriate hardware platforms like microcontrollers or SOCs, system on chips, and developing efficient software. Design tools, testing methodologies, and DFM principles all contribute to a successful design outcome. Embedded systems are already deeply integrated into our lives, and their importance will only continue to grow as technology advances.